Shunsuke, thanks for joining. Can you try to share your screen?
Hi, Prem. Okay,
yeah.
so let me share. Yes. Okay, I think now you can see my screen with presentation mode.
Yes.
Okay.
Thank you. Yeah, it's good.
Okay, it's 3 p.m. So let's welcome everyone welcome back to this session. We have Professor Fukami from University of Tohoku who will be giving his wonderful talk. So whenever you're ready, I think you can start your presentation, Professor. Thank you.
Can you hear me?
Yep, we can hear you very clearly.
Okay, so let me start my presentation. So first of all, I'd like to thank the organizers for giving me this opportunity. I'm really happy to share with you our works on the probabilistic computing with Spintronics. And I think that because I attended ICMAT this June and gave a talk on a very similar topic. So I guess that some of you heard my presentation before, but for such a audience, I hope that you will refresh your understanding. Okay, so I will talk about a new type of the computing based on the stochastic dynamics of the spintronic devices. Okay, so this is the outline of my talk. So firstly, I will give a brief introduction to spintronics and from the conventional spintronics to the unconventional spintronics. And after that, I will describe the spintronic probabilistic bit, P bit. That is the fundamental building block of the probabilistic computers. And then I will show several examples of the proof of concept of the spintronic probabilistic computer or P computers. And I will show you our demonstration of the combinatorial optimization, machine learning, and quantum simulations. And after that, I will switch the gear and talk about the device technology. So I will describe how to enhance the device performance. And then I will describe the projected performance of the computers using the enhanced device, the improved device technologies. And finally, I will summarize my talk. Okay, so let me start from the introductions. So I think I do not have to spend many words to explain the non-volatile magnetic tunnel junction because everybody knows well about it. So the magnetic tunnel junction or MTJs can store the information in a non-volatile fashions, and whose state can be switched by applying the current through these tunneling barriers. And this magnetization direction can be switched by the current and detected by measuring the resistance. And this can store the informations in non-volatile fashions, and also it can operate in a fast speed. And also it has a high endurance and scalable, and it can be operated with the low voltage. And also it has a good compatibility with the back-end brain process of the CMOS technologies. And with these features, the STT-MRAM has been commercialized since around 2018 with the scale of megabit to gigabit. So these are already utilized functionalities in the magnet-resistive random access memories and the semiconductor conventional deterministic semiconductor technologies based on the von Neumann architectures. But in addition to these already utilized functionalities, the spintronic systems has a potential to show the potential has unexplored functionalities that includes analog memory or analog digital tunabilities or short-term memory functionality, linearity, and stochasticities. So we are working on the unconventional computing by fully utilizing these unexplored functionality in addition to these already utilized functionalities. So today I will focus on the stochasticity of the spintronic devices that is useful for the computationally hard problems. Okay, so now I will describe the spintronics p-bit that constitutes the probabilistic computers. Okay, so this is a famous work done by Tohoku University about more than 10 years ago. And so we showed that the cobalt iron boron MgO-based MTJs can show the perpendicular magnetic easy access by reducing the thickness of the cobalt iron boron. By doing so, the perpendicular interfacial anisotropy has been enhanced. And we showed that with these material systems, a reasonably high thermal stability factor can be achieved, and its magnetization direction can be switched by applying the current, and it shows a reasonably large TMR ratios. But for the probabilistic computers, we need to reduce the hopping between these two state 0 and 1, and this can be achieved by reducing the thermal stability energy barriers E with respect to the thermal agitations. And indeed, by increasing the thickness of the cobalt iron boron, we could observe the random telegraph noise from the stochastic magnetic tunnel junction as shown here. So using this stochastic magnetic tunnel junction and using this unit circuit, we can construct a probabilistic bit or p-bit. And this shows the measured time averaged output voltage as a function of the input voltage. And these three panels shows the time domain signals. So at the voltage of the input voltage of 1.95 volt, we observe the equal fluctuation between 0 and 1. And by reducing or increasing the input voltage, we can make the output 0 dominant or 1 dominant state. And this time averaged output voltage can smoothly changes with respect to the input voltage, and this behavior can be well fitted by the sigmoidal function. So this means that this spintronic p-bit can function as stochastic neurons, and in other words, this unique circuit can serve as the poor man's qubit. And the meaning of the poor man means that this system do not have to be operated at reduced temperature, so it can work at the room temperatures, and also its size should not be so large, so we can create this spintronic p-bit with a relatively low cost. Okay, so let me summarize the features of the spintronic p-bit compared with the other solid-state circuits, devices, and quantum bits. So firstly, the spintronic p-bit has a nanometer scale size, so it is favorable for large-scale computers. And also it uses thermal agitations, so it is effective to construct a low power and asynchronous computers. And also its fluctuation speed can be, in principle, reduced down to nanosecond time scale, so the fast computation is possible. And also it can be operated at room temperature, so it has a potential various applications. And also each p-bits can be interacted in an electrical means, so it means that no auxiliary bits are necessary for the computations. And also as in the case for the STT-MRAMs, it has an excellent CMOS process compatibility, so it is easy to manufacture. So these are the features of the spintronic p-bit, and using this spintronic p-bit, we demonstrated several functions that the classical computers are not readily address. So these are the hard problems for the conventional computers. So the combinatorial optimization is kind of the computation task to optimize from the various options. So this is a map of the Tohoku region in Japan, and the traveling salesman problem is a famous combinatorial optimizations, and that's the task to find the shortest route to go around these spots and return to their origins. So this is a very famous hard problems for the conventional computers. And the machine learning is something like this. So this shows the cartoon of the spin glass, which has spins which are randomly dispersed in this matrix, and its spin directions are quenched by satisfying the interaction between each spins. And the machine learning is a task to find a Jij, so the interaction between each spin. So if you are given these spin structures and find the Jij from this spin structure, that's a very difficult task. So if you, so this is a very hard problem for the conventional computers, but it is also useful for example, face recognitions. And regarding the quantum simulations, it's not easy to obtain the quantum wave functions to satisfy the several conditions. So the one-dimensional transverse field Ising model is a famous quantum problems, and that is not readily addressed by the classical computers. So we need to use a high-performance computer to simulate the quantum problems. Okay, so first, and we addressed these problems by using the spintronic P computers. Okay, so let me first describe how to address the combinatorial optimization by using the probabilistic computing. So For the process solve the combinatorial optimization by using the quantum annealing or simulated annealing, we first need to define the cost function from the given problems. And after that, we reduce the temperature, and then the system converges to a certain state. And from the converged state, we can know the answers as the converged state. So this is the case for the quantum annealing or simulated annealing. And for the case of the probabilistic computing, as in the case for the quantum or simulated annealing, we first need to define the cost functions, and then we have to keep the temperature high enough so that it can scan this every state and take the statistics. Then, as the time goes by, we could obtain this kind of the histogram, so we can know the lowest energy state that corresponds to the answer for the given problem by the most probable state. So this is a scheme to address the combinatorial optimization using the probabilistic computing. Okay, so this shows the block diagram and photograph of the constructed probabilistic computers using the 8 stochastic magnetic tunnel junctions here. And these stochastic MTJs are interacted by using the Arduino microcontrollers. So each p-bit fluctuates in time, and so depending on the state of each p-bit at each time, the microcontroller calculates the feedback signal to reduce the total energy of the given cost functions, and so repeat this cycle. So we watch this system and take the statistics, then we can know the answers. Okay, so I would also describe the cost function or the energy for the integer factorization. So in this experiment, we chose an integer factorization as an illustrative example of the combinatorial optimizations. So this shows the energy or cost function to solve the integer factorizations. So large F is the number we would like to factorize, and large X and large Y are the factors we would like to obtain. And large XY can be represented by this binary form. So the small x1, x2, x3, y1, y2, y3 can be represented by our p-bit that can take the value of 0 or 1. So by using this equation and these p-bits, we can scan all the possible combination of the x and y, and so we can in principle obtain the answers by the lowest energies. So for the case to factorize 35 using 4 p-bits, so if we substitute these numbers to these equations, the energy can be represented as shown here. So here we have one important point. So there are 3-body interactions and 4-body interaction terms in this energy or cost function. And this is not easy for the quantum annealing because it requires a close interaction between each qubit. But for the case of the probabilistic bits, it can be interacted electrically. So this kind of the 3-body and 4-body interaction can be easily implemented in the systems. So to reduce the total energies, the input we need to send to each p-bit can be calculated by the derivative of the energy by the state of each p-bit as shown here. So what we need to do is just programming these interactions to the microcontrollers and send the feedback signal to each p-bit depending on the value of each p-bit at each time. Okay, so let me show the results. So first we tried to factorize 35 using 4 p-bits. So before turning on the interaction or correlation between each p-bits, systems shows an equal probability from 1 by 1 to 7 by 7. But once we turned on the interactions between each p-bits, we observe the highest peak at 5 by 7 and 7 by 5, which are exactly the factor of the 35. So next we try to factorize 161 and 945 using 6 and 8 p-bits, and we could observe the highest peak at the correct positions. So this means that the our probabilistic computers can address the combinatorial optimizations. Okay, so next, let me talk about the machine learning. So for the case of the combinatorial optimizations, the synaptic weight or the interaction between each p-bit are fixed. But for the machine learning, we would like to obtain the Jij or Wij that can satisfy that can lead to a good distribution of the p-bits. So we have to change or update the synaptic weight Wij. So we need one more functions, so learning rule and weight update mechanism. So according to the Boltzmann machine concept, the update of the synaptic weight can be done by these equations, and this function can be implemented by the RC circuit here. So the RC circuit compare the ideal distribution of the p-bit, ideal distribution of the output of the p-bit, and the current distribution of the output of the p-bit. And based on the difference, this RC circuit update the synaptic weight and so send back the signals. So by repeating these cycles, the system converges to the correct answers. Okay, so these are the experimental results of the Boltzmann machine using the probabilistic, stochastic MTJ-based probabilistic computers. So at the beginning of the experiment, so we tried to learn the input and output relation for XOR gate and full adders. So at the beginning, we observed so this distribution doesn't make sense, but at the final of the iterations, the system converges to this state. So this is exactly the expected distribution of the XOR gate. Because for the XOR gate has two inputs and one output. And if the input is 0, 0 or 1, 1, the output should be 0. And if the input is 1, 0 and 0, 1, the output becomes 1. So through these iterations of the learning, the RC circuit and the synaptic weight logic learn the input-output relations for the XOR gate. And the same thing can be observed for the full adders. So this experimental results means that the Spintronic-based probabilistic computers are also capable of addressing the learning or machine learning. Okay, so finally, let me talk about the quantum simulations, so simulating quantum problem using the probabilistic bits. So as I mentioned, the one-dimensional transverse field Ising model is a famous quantum problems that is not easy to address using the classical computers. So, and to solve the quantum problems, the one way is using the qubits, but there's another way to use a classical bit or probabilistic bit using the Suzuki-Trotter decompositions. So according to the proposal by the Dr. Suzuki, the quantum bit can be represented by a several number of the digital bit, classical bit or probabilistic bit using these equations. So the one-dimensional transverse field Ising model translates to the two-dimensional nearest neighbor classical Ising graph by using the Suzuki-Trotter decomposition. So using this scheme, we simulated the a one-dimensional transverse field Ising model using our probabilistic computers. Okay, so let me show the results. So, so in this experiment, we applied the annealing scheme to find the solution of the quantum problems. So we observed the convergence of the systems to a particular state. And the right figure is important. So the orange bar shows the probability of the converged state. So for the first 32 highest probability states. And so the blue bar shows the exact ideal distribution of the each states. So at least the highest, so the first and second probable state can be reasonably reproduced by the Spintronic-based probabilistic computers. So we observed a good agreement with the exact many-body quantum distributions. So this means that the probabilistic computers are also capable of addressing the quantum problems by using the Suzuki-Trotter decompositions. Okay, so now let me change the topic and describe the device technologies. So as I mentioned, these computationally hard problems can be addressed by using the probabilistic computers. So the future challenge is that these systems has a very small number of the p-bit, but it requires a relatively long computation time. So we have to, so in future, we have to increase the scale of the computers and reduce the calculation time. So we need to increase the sampling throughput of the probabilistic computers, and this can be translated to our language that we need to reduce the relaxation time of the stochastic MTJs. So we tried to reduce the retention time from millisecond to ideally nanosecond. So we have to make faster, the fluctuation faster for large-scale problems. And initially, we thought that the reducing the relaxation time can be achieved by reducing the thermal stability factor E over kBT, but we found that this is not complete to reduce the retention time or relaxation time. So let me show our calculation results. So we performed the micromagnetic simulation for the perpendicular magnet and the in-plane magnet. And these two systems has the equal thermal stability factor of 3.8. So E over kBT is 3.8 for both systems. But the perpendicular easy access systems is uniaxial, whereas the in-plane easy access has the three different axes with different energies. So for the in-plane magnet, if you'd like to rotate your magnetization in this XY planes, you need to apply 10 millitesla. But if you'd like to rotate your magnetization in the out of the planes, you need to apply 100 millitesla. So this is not uniaxial, but the three axes are different with each others. And these are the calculated random telegraph noise. So the fluctuation speeds are largely different between these cases, although the thermal stability factor are exactly the same. So making long story short, what we found is that the tau zero, the attempt times are largely different between these two cases, and this attempt time can be dominated by the slope of the potential well. And because the in-plane magnet has the steep slope due to this hard axis, so negative anisotropy along the out of plane, and this leads to the reasonably short tau zero, and also the thermal stability factor can be reduced by reducing the in-plane anisotropies. And based on this concept, we fabricated the in-plane stochastic MTJs, and indeed, we observe very fast nanosecond fluctuations. Okay, at the last of my talk, I would like to describe the expected performance of the probabilistic computers. So here we compared the power and throughput to execute a probabilistic algorithm on various computing hardware. And the N1 to N4 denotes the reported results for the NVIDIA's GPU, and G1 and G2 denotes the reported values of the Google's TPUs. And we constructed FPGA-based probabilistic computers without using the stochastic MTJs, but its performance is already here, so it shows a reasonably low power consumption. It has a similar sampling throughput. And if we use a nanosecond fluctuating stochastic MTJs plus megabit scale integration technologies, the expected value is located around here. So we can expect a much higher sampling throughput and a much lower power consumption compared with these reported value for the deterministic computers. Okay, so let me summarize my talk. So as I mentioned, the probabilistic computing is promising to run a probabilistic algorithm for computationally hard problems, and stochastic MTJ is suitable for the probabilistic computers. And we demonstrated that combinatorial optimization, machine learning, and quantum simulations by constructing the proof of concept systems of the probabilistic computers with stochastic MTJs. And we also studied the physics of the stochasticities, and theory predicted that the in-plane systems allows to engineer tau zero and Ioba cavity independently, and the experiment shows that the 8 nanosecond fluctuations can be possible. And so by applying the nanosecond stochastic MTJs plus MRAM's current MRAM's megabit integration technologies, we could expect efficient hardware for probabilistic algorithm. Okay, that's all. Thank you for your attention.
Okay, thank you very much for the wonderful talk, Professor. So we'll have a short Q&A session. If anyone has any question, we can take maybe 1 or 2 questions.
Hi, Prof.
I would like
Thank
to.
you.
Durgesh, go ahead.
Thank you for the nice talk. So for the first part, combinatorial optimization problem, I mean the energy is the deciding factor. So I was wondering how do you generally come up with that expression of energy?
I see. So how we can determine this energy or cost function?
Yeah, that's right.
I see. That's actually, I don't know, but many people studies for example, quantum annealing systems or the classical annealing systems. So we can basically use the same cost function. And so the computer scientist studies the form of the energy or cost function for a various kind of the computationally hard problems. So we can use exactly the same expression for our probabilistic computers.
Thank you, Prof.
Thank you, Shunsuke, for a very interesting talk. It is very impressive. So my question is, it looks like you have almost completed the proof of concept. Are you in talk with any foundries to make chips?
Chip, real chip.
Yeah.
Actually, we have a plan to, we would like to integrate the stochastic MTJs on CMOS circuits. So actually, that's exactly what we would like to do in near future, in the next several years.
Very impressive. Thank you.
Okay, thank you very much, Prof. Fukami, for your wonderful talk. So next, we will have Professor Muduli. Are you here? Yeah, okay. So he will be giving a talk on non-trivial spin orbit talk with non-cornelia antiferromagnetics. Okay, so whenever you are ready. Thank you.
Yes, I'm ready. But can I share the screen? I think, okay, now I can, I guess, let me see. Okay, do you see the screen?
Yeah, we can see very clearly.
Okay, maybe I just a minute. Okay, so shall I start?
Yeah, please go ahead.
Okay, so thank you very much for inviting me to give this talk, and also in particular, thanks to Prem for giving this opportunity. So I would mainly talk about, I changed the title a little bit because there are two none. So I made the first one as unconventional spin orbit torque using non-collinear antiferromagnets. So I'll start by very briefly discussing about what is spin orbit torque. Okay. So spin orbit torque basically started in the year around 2010 and 11, where Fetio Gambardella group showed that if you have a bilayer structure mainly consisting of platinum and cobalt, then you can drive the domain wall by means of current, or you can even switch the magnetic layer by passing the current. So this lead to this basically the starting of the field of spin orbit torque. And later on, Dan Ralph group showed that you can even tune the line width of the resonance, or which is related to the damping constant of the material by means of current in this structure consisting of permalloy and platinum. All this has give rise to the area of spin orbit torque, and the origin of the spin orbit torque can be described by means of a charge current, which is if you flow through the platinum, for example, and this charge current will split, and there will be opposite kind of spin at the different at a direction 90 degree to the flow of charge current. So this is known as the spin Hall effect. This is a bulk effect, and it's mostly observed in the heavy metal like platinum, and it is proportional to the spin orbit coupling. But the important point for this talk is that the charge current is flowing along the x-axis. There is a spin polarization along the y-axis, and the spin current will also flow in the z direction. Another effect which can also lead to spin orbit torque is so-called Raspa-Eidenstein effect. And this Raspa-Eidenstein effect arises from the interface between, for example, ferromagnetic heavy metal. There is a broken inversion symmetry, and this leads to spin splitting of band and spin momentum blocking, and a band structure which looks like this. And consequently, when you apply current, the Fermi contour will shift in a manner that will generate a spin accumulation. The spin accumulation in this case is also perpendicular to the direction. The charge current, suppose the charge current is like that, the spin accumulation will be along y in direction, which is the same as that of the spin Hall effect. So both these lead to so-called conventional spin orbit torque, and the conventional spin orbit torque can be determined from this technique called spin torque ferromagnetic resonance, where you pass a RF current and detect a DC voltage. And this leads to, if you look at the DC voltage that you detect using STFMR, the angular dependence of that has a sine to phi cos phi dependence. So first of all, the line shape of this STFMR has two parts. One is symmetric part, which is shown in the green, and the antisymmetric part, which is shown in the blue. And both these components will change sign if you reverse, for example, the magnetic field direction by 180 degree. Or you reverse the direction of the field, you can see that there is a sign change, and the magnitude also doesn't change. And this is a consequence of the fact that this has the sine to phi cos phi dependence. By the way, the sine to phi part basically coming from the AMR, because this voltage is detected due to the AMR in this structure. So this is an indication of conventional spin orbit torque, where the charge current flowing along the x-axis, the spin current flows along the z direction, and the spin polarization is along the y direction. So this is shown in this figure here. And this can be, for example, if you do a detailed angular dependence, for example, this is for tantalum, you see this nice sine to phi cos phi dependence, both for symmetric as well as for the antisymmetric component. Here, the sign of the symmetric and antisymmetric component are different and opposite because the spin Hall angle of tantalum is negative. This is an example from our lab only. So now the thing is that when you go to other materials, and people have shown that this conventional, there can be something called unconventional spin orbiter. And here I show some examples. There has been many reports by now which shows unconventional spin orbiter. The first one here is from non-collinear antiferromagnets, where they have shown that you can get spin polarization which is out of plane as well as along the x-axis, which is along the current direction. And in this example, back in 2017, they have used the broken crystal symmetry of WTE2 to show that there is a unconventional spin orbiter. And you see here in this STFMR data where the sine to phi cos phi dependence is no longer there. They saw it in the case of antisymmetric component. And there is an additional unconventional torque present in the system because of the broken crystal symmetry. And so why we are interested in this unconventional torque is because this unconventional torque can lead to out of plane spin polarized current. And this can then be used to switch the perpendicular magnetic system, which are mainly used in the magnetic recording. So here is an example I have shown. There are many examples, but this is one example where they have used this tungsten ditelluride, and they're able to switch at zero field. So because if you have a conventional torque, in order to break the symmetry, you need to apply in-film field. But if you have unconventional torque, you can achieve zero field switching, as they have observed in this example here. And here it was done with the high crystalline, low crystalline symmetry of WTE2. Similarly, another report recently has used this non-collinear antiferromagnet MN13, and using this MN13, they are able to generate out of plane anti-damping like torque, and then achieve zero field switching this way. So that's why this unconventional talks are very interesting. So in this talk, I will show observation of some unconventional spin orbit torque in non-collinear antiferromagnetic systems, and I will in particular discuss these two systems, IRMN3 and MN13. Both are non-collinear antiferromagnet. So let me start with IRMN3, and the basic reason why we are interested in antiferromagnets in general. For Spintronics, I think previous speakers have already talked about that. So it's because they have net zero magnetic field and they offer faster dynamics. So you can pack it's because of the net zero net magnetic movement. So the storing information can be much more higher density. The dynamics is faster and so on. So in particular, I'm going to discuss about this MN13 and MN3IR, and the crystal structure of these two metals is shown here. And there has been already a lot of work on these two materials. So here they have this structure which is non-collinear antiferromagnet. So the magnetic moments are not 180 degrees to each other, but they have certain angle, but the net magnetic movement is still zero. And they have this so-called Kagome lattice, which I will discuss in more detail later on. And in particular, let me start with IRMN3. And there has been one work before, in fact, from Singapore only, where they have shown that you can use the magnetic asymmetry of IRMN3 to generate unconventional spin orbit torque. And here they have used certain very high quality epitaxial IRMN3 films with L10 and L12 phases. And as you can see, their angular dependence shows slight deviations from the sine to phi cos phi dependence. And they attributed that this is due to this magnetic asymmetry found in this IRMN3. So in our case, we tried to grow this IRMN3. And in our case, we found that we grow actually polycrystalline films. And we first optimized the growth of IRMN3, and we somehow formed the gamma phase because we use the silicon substrate in our case. So, and the gamma phase, however, does not have this magnetic mirror symmetry. or magnetic mirror or low magnetic mirror symmetry. They do not have this low magnetic mirror symmetry. So in this case, we do not expect an unconventional torque from the bulk crystal structure of this material. But in addition, we have also polycrystalline films. So let us see, we can see unconventional torque in this system or not. So first of all, we grow different kind of materials, different kind of multi-layer stacks. The first one here is permalayer, and on top of that, we grow this gamma phase of IRM3, and this is lead to some produce of exchange bias. But if you grow in the reverse stack, then there is no exchange bias. So if you first grow IRM3 and then permalayer, we do not get any exchange bias. Then if you introduce between this permalayer and gamma IRMN3 copper layer, then the exchange bias disappears. So we want to see whether this exchange bias also affect the STFMR measurements. So these are the results, the STFMR results. You see that in the first case here, when the gamma IRMN3 is on top of permalayer, we see a symmetric component and an antisymmetric component. But strangely, the symmetric component shows a sign change, but also a change of magnitude when you reverse the magnetic field. So this is an indication that there is some unconventional torque is present. And the same thing is happening with the antisymmetric component as well. Now, when you remove the exchange bias by removing the stack, by reversing the stack sequence, we still see unconventional torque because you can see that symmetric component also shows a change in magnitude as you reverse the magnetic field, which is not expected for a conventional spin orbit torque. Now, if you introduce copper between these two, then this unconventional torque more or less disappear, and now we have the standard conventional torque here. So this indicates that the unconventional torque that we observe here is of interfacial origin, and because it happens only when there is the permalayer is in direct contact with IRMN3, and it is independent of the sequence, how it is. So independent of that means it is independent of the exchange bias as such. So this is indication that this is interfacial origin. We further verify this by means of angular dependent measurements, detailed angular dependent measurement of symmetric and antisymmetric component, where you see that there is a significant deviations from the sin 2 phi cos phi dependence, both in the symmetric component and the antisymmetric component, whenever the permalayer is in direct contact with iridium manganese. Doesn't matter the stack sequence. And when you have a copper, then you have the standard sin 2 phi cos phi dependence, indicating that here it is conventional torque, but where it is unconventional torque in both these cases. And in this case is attributed to the interface. So this is a summary. So what we see that whenever the IRMN3 is in direct contact with permalayer, we see a polarization, both out of plane polarization as well as X and Y polarization. Y is the one which is conventional, and that is observed in the copper case when the copper layer is there. In all other cases, we are seeing all the directions of polarization. And so this leads to a conclusion that this is actually a substantial out of plane polarization, that in out of plane torque that we are observing, and it is related to the interface. And in fact, after we published this paper, we saw another paper in PRB, which also related to similar conclusion in the same metal system, that it is the out of plane spin polarization is actually related to the interface. Now I will change the material and I will go to another non-collinear antiferromagnet, which is known as Mn13, and this also happened to be wild semi-metal, and it's a quantum material. And now, although it is an antiferromagnet, it exhibits anomalous Hall effect, anomalous Nernst effect, and magnetic optic Kerr effect, which are the effects normally observed in ferromagnets. And this is related to the fact that this is a special metal which exhibits so-called wild points near the Fermi energy, as has been observed in experiment. And this wild point leads to a large Berry phase curvature, leading to these anomalous transport properties in this material. So if you look at the crystal structure of Mn13, it has this Kagome lattice in the C plane. and it is this manganese spins shown in the red. You can see that they are 120 degree to each other, and this leads to a net zero magnetic moment, but they are not collinear. So this has this Kagome kind of crystal structure. In fact, previous speaker, Professor Fukami is an expert in the MN13, although today he presented work different to that, but he has done some groundbreaking work in this material as well. Here I will show you some of the previous work that has been done, which actually motivated us to work on this area. Was the discovery of the so-called magnetic spin Hall effect in 2019, where they saw that they were performing inverse spin Hall effect measurement on bulk MN13, and they saw this symmetric component doesn't change the sign as you reverse the direction of the field, and this was attributed to the magnetic spin Hall effect. Now, but we are interested first of all on a normal spin Hall effect, which was calculated. There was a theory typical back in 2017 where they had calculated spin Hall effect in several non-collinear antiferromagnets, including MN13, where they had found that there is a substantial spin Hall effect in this material, which is independent of spin orbit coupling, but it appears because of the magnetic texture in this material. And there were previous works which actually showed the experimental work which showed evidence of spin Hall effect. In this one for a nanocrystalline MN13, they had found some spin Hall conductivity for MN13. And here also there is another work on polycrystalline MN13. They had also observed a spin Hall effect. But there was no work on C-plane MN13. So we tried to grow epitaxial C-plane MN13. And we found that if you use a ruthenium seed layer and a substrate, sapphire substrate, then we can grow epitaxial film. And so this growth optimization is not as simple, but we optimize finally. And these are the optimized conditions after which we could get epitaxial thin films. And this is showing some different thicknesses that we have nice epitaxial thin films. And this phi scan confirm that the epitaxial film, and this is the epitaxial relationship. And also the AFM roughness shows the AFM measurement so that the surface is very smooth. And then subsequently, we also do a composition mapping to confirm that we have formed the perfect stoichiometric composition, and there is no clusters of manganese, because that has been reported in the literature. So we see that this is a manganese and tin distribution are rather uniform throughout the film, but there's a little bit of excess manganese. It's not that much, but there's a little bit of excess manganese present in our films. And this is a magnetization measurement, shows that the magnetic moment is really, really small. This weak magnetic moment comes with the fact that the magnetic moments are a little bit tilted out of plane. So it is not it behaves like a very weak ferromagnet, although this is an antiferromagnet as such. But this magnetic moment is really small. And then we did deposition of permalloy on top of that, and then do FMR and inverse spin Hall effect measurements. These are the FMR measurements from which determine Gilbert damping constant and M effective. And most important, this inverse spin Hall effect, where you see that very nice symmetrical curve which changes sign, which is indication that this is due to the spin Hall effect. And when you do the thickness dependence and you fit it, you can calculate spin Hall angle and spin diffusion length. The spin diffusion length is found to be 0.42 nanometer, which agrees with what literature has reported. But the spin Hall angle is found to be, first of all, negative, and it's quite large compared to what has been reported in the past for polycrystalline and nanocrystalline films. So the theoretical value, however, is positive and is around this value. Our value is negative, and we explain this on the basis of the fact that there is a shift of Fermi level in the actual sample, which can lead to the sign change and increase of the magnitude of this of the spin Hall conductivity. So then we looked at spin orbit torque, and for that we need to make devices and then pass RF current. And these are some example of STFMR measurements on the same sample. So you see that as you reverse the direction of the field, the symmetric component shown in blue does not reverses the sign. So this is an indication that there is some unconventional spin orbit torque present in the sample. So in order to understand the origin of this unconventional spin orbit torque, we did what we did is we tried to pass RF current in different crystallographic directions of Mn13 because Mn13 in our case is epitaxial. So here the RF current is perpendicular to this particular in-plane direction. And here we see that the torque is conventional because the both symmetric and antisymmetric component follows sin 2 phi cos phi dependence. But if you pass a current in the 90-degree or in parallel to this particular direction, then we start to see unconventional torque because now the symmetric component no longer follows the sin 2 phi and cos phi dependence. So this is an indication that this unconventional torque in this system is coming from the crystalline structure of this Mn13. And furthermore, we did thickness dependence. Now, in the thickness dependence, we found that there are two, the conventional torque, which is shown in the orange plot here. It is actually, first of all, has opposite sign the moment Mn13 is present. So it indicates that this is a torque coming from the presence of Mn3, not just due to formulae. And then it increases and kind of saturates. So which is a behavior similar to spin Hall effect. And if you look at the unconventional torque, which is shown in this green, this actually increases and it just keep increasing. So there is no sign of sign of saturation. So this both this indicates that this is actually arising from the bulk Mn3, and this is different to compare. There was a recent paper published very recently from Stuart Parkin groups where they had done similar measurements. And there they also saw this unconventional torque, and they say that if you vary the manganese 3 concentration, then there is this unconventional torque is kind of constant. It doesn't change with the thickness for the range of thickness they has studied. But in our case, it actually there is showing a increase. So we are attributing this to bulk Mn13 rather than the interface, which was attributed in this paper. So this thickness, both the thickness dependence as well as the orientation dependent support the fact that bulk origin of unconventional spin orbit torque in Mn13 system. So with that, I will just summarize, make a brief summary that we saw this unconventional spin orbit torque in a system consisting of non-collinear antiferromagnets. In the case of iron Mn3, it arises from the interface, whereas in the case of Mn13, it arises from the bulk and it's anisotropic in nature. And with that I conclude, and this work that I presented here was mainly done by Pankhuri and Himanshu, who are PhD student and completing near to completion of their PhD thesis. So thank you very much for your attention.
Okay, thank you, Professor, for your wonderful talk. So now we have a short Q&A question. So if there's anyone with a question, you can unmute yourself.
Hi, Prof. This is Durgesh. Thank you so much for the talk, for the nice talk. So I actually wanted to ask that when we try to use these antiferromagnets for switching, for example, generally we see that it doesn't. I mean, it is not able to switch fully. For example, the perpendicular magnet which is on the top. So any thoughts to improve this switching efficiency in these antiferromagnets?
Well, I mean, there are reports already that claim that they have achieved switching, zero field switching with antiferromagnets. So it is depends on how you optimize. For example, if you want to use Mn13, these measurements that I showed you indicates that you have your current direction has to be in particular crystallographic direction. Then only you will produce this unconventional torque. And then only you can switch. But if you make a polycrystalline Mn13, and you probably cannot switch it.
Yeah, that's right. Yeah, but I was wondering, I mean, it can switch at the zero field, but
Mhm.
it may not be able to switch fully. For example, for magnetic spin Hall effect, it depends on the domains present in the
Then the switch, whether it is switching fully or not, that depends on the ferromagnet, that also what is the domain structure of your ferromagnet.
Okay, thank you.
We have also, even in the case of cobalt platinum also, we haven't full switching when you look at it. But I think it depends on many factors. But I will say that the domain structure of ferromagnet is more important in that case.
Okay, thank you, Prof. Thank you so much.
I have one question.
Yes.
Yeah, thanks, Prof, for your nice, interesting and talk. So my question is regarding the energy consumption. Like field free has been achieved, but because the platinum, of course, there is an issue of bottleneck, which is like a field free switching. But from the energy perspective, what are the current densities required for switching these kind of materials? I mean, if you use these antimagnets.
Yeah, I think you are referring to that. Maybe I go to slide, some previous slide. You are probably referring to this. No, maybe it was, sorry. Yeah, this one, I guess, right? So here, this is the paper which have achieved zero field switching. So the current density they claim is lower, 10⁶ ampere per centimeter square, which I think is lower than cobalt platinum.
Yeah.
At least this was the claim. But we have also tried to do something similar, but even to get the PMA on top of MN13 is not that straightforward. You have to optimize it properly. And so this probably has a result of large optimization of the sample, which lead to this lower threshold current density for switching.
Yeah, thanks.
Thank you for the interesting talk. I have two questions. Firstly, whether your iridium manganese have any AHE? You mentioned that MN3SN shows AHE. Does your iridium manganese also show AHE?
Iridium manganese we haven't investigated as such because these are polycrystalline form, and it should exhibit AHE, but there I think I'm not sure about that. For example, in MN13, if you grow C plane, it doesn't exhibit AHE. But if you go polycrystalline or any other orientation, it will exhibit AHE. That is in agreement with what literature has shown. But C plane doesn't exhibit. So MN13, MN3 IR being similar, I think the same is true there. But we were looking for literature once, and I think we didn't find a clear answer to this question. But it's an interesting point. We haven't, since we didn't make epitaxial, so we didn't try to measure.
So secondly, you showed exchange bias in pomalloy iridium manganese. Were they as deposited, or you did some field annealing?
It actually grown with certain field. It was grown. There is a inbuilt magnet in the sputtering system which was used, but I don't think that is important. Although we happened to keep it on because that field, the inbuilt magnetic field is very small. It's like 150 Gauss or something. So what we found that it is probably the stack sequence which is more important to get exchange bias rather than that inbuilt field. But we haven't done the very systematic study to confirm, clearly say that what is the reason for it.
Okay, thank you.
Okay, if there are no other questions, I guess this is the end.